Example number 2, known cross sections, figuring out volume problems. Again, this process is new, and I think what's critically important is for you to see these pictures. So what we're doing is figuring out the volumes of shapes like these that are built upon a specific foundation, and they are designated a specific shape, like semicircles or squares or rectangles or triangles. So I need to know how to find the volumes of each of those. This example is going to work with equilateral triangles, and it's kind of a tougher shape, but I think after we get finished with setting up the integral, we're going to lean on our technology to solve it the rest of the way. But we'll need to have a little knowledge and revisit our knowledge of special right triangles, 30-60 right triangles specifically, as we go through this problem. So let me fast forward to example 2 so that you can take a look along with us. Alright, so here is example 2. We're talking about finding the volume, this time of a solid whose base is bounded by the graphs of y equals x squared and y equals 2 minus x squared. The cross sections this time are going to be perpendicular to the x-axis as well, and are equilateral triangles. So let's first of all look at the foundation that we are going to build upon. I'm talking about y equals x squared, which you all are aware looks like that, and y equals 2 minus x squared. Let's contemplate that. This is a parabola that opens downward that is translated up 2 units. So hopefully you can see visually what's going on here. Now I highlight these intersection points from -1 to 1 and from +1 to 1, as those intersection points will dictate our integration limits. And since we are integrating perpendicular to the x-axis, we will steal the x coordinates here with our integration. So that's the foundation on which we will build these equilateral triangles. So the same type of axis system, now I'm going to build it in an XYZ coordinate space. I'm just going 2 units in the y direction, just as you're looking at to the left here, and 1 unit both to the right and left with the x's should be fine to accommodate these graphs. So now the task is again to place these intersecting parabolas onto this XYZ coordinate grid so we can see the foundation on which to build these equilateral triangles. Alright, so here comes the 4 critical locations that you also see on the left at the origin, and the order pair 1, 1, the order pair -1, 1, and the order pair 0, 2. This is the first parabola, the one that opens upward on an XY coordinate grid, still opens upward here on our XYZ coordinate space, upward so to speak. Just have to get visual with what's going on here. Hopefully before I even draw it, you know what I'm going to draw next is this parabola that opens downward, and I'm talking about downward toward the x-axis. Here's what that parabola would look like. Kind of have to draw this big in order to allow yourself to see these triangles that will be built on this region of intersecting parabolas. So hopefully we can take a look here and this will make sense to you. Here's one equilateral triangle, okay? So if I show it to you again, the first line is parallel to the y-axis, and then equilateral triangles, you're going, I know how to draw an equilateral triangle, and it sure as heck doesn't look like this. Well, it does in perspective. So really that third side is nearly, not completely, but nearly vertical like the z-axis. Okay, so as I build some further triangles, I think you'll be further convinced. But let's look at triangle number 2. Again, first line parallel to the y-axis. That one stretches a little more than you feel comfortable with, I realize. But if you come down, you'll see that equilateral triangle drawn in perspective. There's your third. There's your fourth. I'm just drawing some hidden lines in there to sharpen things up a little bit for clarity's sake. Alright, so I've drawn 4 equilateral triangles, and now the triangle sides will begin to taper down a little bit. Again, I'm going to look at theoretically an infinite number of these equilateral triangles, bookshelved from -1 to +1. Alright, let's see how this integral is going to come together. So again, I'm integrating from -1 to +1 some area formula. Well, let's contemplate the area formula here. I know how to find the area of any triangle. It's 1/2 base times height. This triangle has a side length dictated by the intersection of these 2 parabolas. So what I've done here is factored out the 1/2, leaving the integration from -1 to 1, and I still have that base times height dx. Let's talk about an equilateral triangle. All 3 sides are equal in length. Well, the side length here is going to be the top parabola minus the bottom parabola. The side length of the equilateral triangle is going to be equal to the top parabola, 2 minus x squared, minus the bottom parabola, minus x squared. I gotta pause here. This is extremely important. Unless you're able to figure out the side length for each equilateral triangle, which will be determined by the top parabola minus the bottom parabola, you're not going any further with this problem. So you have to take a look at this and take some time and understand where this comes from. What you're looking at is one side length of this equilateral triangle determined by the top parabola minus the bottom parabola. If we go back and look at our previous screen, you see each of these triangles, how that bottom base is determined by the top parabola minus the bottom parabola. So we are just now making the math that agrees with that statement. So let me catch us up here. This is the area formula, kind of transforming to our exact scenario. And I know that the one side of the equilateral triangle is 2 minus x squared minus x squared. Well, when combining like terms, I can simplify this to 2 minus 2x squared. Now, what happens if I drop an altitude and cut 2 minus 2x squared in half? I hope you would agree that that yellow distance is equal to 1 minus x squared. What are you doing this nonsense for? Remember, I got to go base times height. When we're talking about the height of a triangle, we're talking about its perpendicular height. We find that by dropping an altitude. And an equilateral triangle has 3 angles of 60 degrees. Now I drop the altitude, which has created this 30-60 right triangle. You might remember the side length relationships that exist here. If you know the short leg is x, then the hypotenuse is 2x, and the long leg is x times the square root of 3. Well, in this case, our short leg is 1 minus x squared. That's going to dictate that our long leg, or height, is that short leg, 1 minus x squared, times root 3. Ugly, but true. So now I have both the base of this equilateral triangle, 2 minus 2x squared, times the height, root 3 times 1 minus x squared. And of course, all these triangles will differ depending upon where I am within the integral limits from -1 to 1. So again, the base is 2 minus 2x squared. And the height, ugly as sin I realize, is root 3 times 1 minus x squared. Is root 3 times 1 minus x squared. Okay, so now I have that root 3, I can factor that out of the integral to make life a little easier here. I'm going to get not 3 over 2, but root 3 over 2 times the integral from -1 to 1 of, and now I'm performing this first outside, inside, last technique in order to multiply these two binomials together. Allow me to do this quickly, and you can verify that work on your own. Which is very simple to integrate at this time. I know I can get home and integrate that. So I still have the root 3 over 2 constant. And now I'm utilizing the power rule in reverse, going 2x minus 4x cubed over 3 plus 2x to the 5th over 5. And with my evaluation from -1 to 1. So you can at this time integrate this on your calculator or continue here plugging in 1 and then subtracting, plugging in -1. Not too terribly difficult, but when you do this, you'll get root 3 over 2 times, when you plug a 1 in for x, you'll get 2 times 2 minus 4/3 plus 2/5 minus, plugging a -1 in for x, -2 plus 4/3 minus 2/5. Continuing to work here, you still have the constant out front, root 3 over 2. The common denominator here is 15. So we've written all 6 fractions with a common denominator of 15 and can get home from here, hopefully. This is root 3 over 2 times one monster fraction with all 6 terms, which equals root 3 over 2 times 32 over 15. This would be in units squared. Excuse me, this would be in units cubed as we're looking at a volume. So the calculus semi-tough here to set up the integral, perhaps even more difficult dealing with this equilateral triangle and knowledge bank of 30-60 right triangles and figuring out the height in order to arrive at my final integral answer. And remember, you're finding volume, so when the dust clears here, you're talking about this in units cubed. So make sure you keep track of that as you are writing down answers for problems like these. So there's the nuts and bolts of cross sections volumes using cross sections, and something that you'll definitely need to practice upon. So we'll get you some practice work and an opportunity to ask questions further. Take a look again at example 1 if you need to. That's kind of the basics. Example 2 here, a little more advanced. Hope it's helpful. We'll see you next time. Over and out.